practice trig subs, and as obviously some of the complications or wrinkles that can arise. But start out with just the quote-unquote basic version, to the extent that there is such a thing. So let's see, last time we did 1 over x root x squared plus 9. Does that sound familiar? Maybe, okay, I'm saying something else. All right, so let's just do a couple of other examples of the basic version. If I do square root of 4 minus x squared, and then after that we'll do the square root of x squared minus 4. Right? Doesn't look too different, but they end up looking, leading in different directions. Go figure. So again, our kind of slogan, our overall strategy is think Pythagoreanly and sub for an angle. You've got to think about a triangle here. And these, I'm going to think of as squares. This is 2 squared, this is x squared. And in the Pythagorean theorem, the thing that gets subtracted from is the hypotenuse. So I'm going to put the 2 on the hypotenuse. And x on either of the legs. So when I do that setup, this ends up being that third side. Okay. This squared plus that squared is that squared. Okay. So yeah, one of the things I had to recognize to set up the triangle is what goes where. And if you see a minus, right, the thing being subtracted from is the hypotenuse. If you see a plus, the mystery side that you haven't filled in yet is the hypotenuse. All right, sub for an angle, let's say this one. So if I start thinking about the trig ratios associated with theta, I can see that the sine of theta is x over 2. And the cosine of theta is square root of 4 minus x squared over 2. I could write down all 6 if I wanted to, but there's a particular reason to be interested in these two. I'm interested in this because that allows me to solve for x. Right? I'm trying to do this inverse substitution strategy. I know that I'm going to need to write x in terms of theta. And I'm interested in this one because this expression is in the problem, the square root of 4 minus x squared. So I can solve for that expression. Square root of 4 minus x squared is 2 cosine theta. And then I'm going to need dx, which I just get by differentiating x. 2 cos theta d theta. So this is the key information that I need in order to do the substitution. I need x in terms of theta. I need other expressions in the problem in terms of theta, like the square root. I need dx. Once that's all in place, I just sort of drag and drop everything, to where it is over here. So this is 2 cos theta. This is 2 cos theta d theta. And now I've kind of reset. I'm in Trigville, different sort of section of my brain kicks into gear. And I have to figure out how do you integrate the cosine squared. So pulling out my memory related to sine and cosine powers. That's the genre of problem that I have. Powers of sine times powers of cosine. Yes?
Would you do 1 minus sine squared theta and then replace x with 2 sine theta?
Not quite. So if I were to, that's an interesting idea. So cos squared theta is 1 minus sine squared theta. And so cos squared theta turns out to be 1 minus x squared over 4. So if I plop that into the integral, I'm going to end up with this. But that's a problem, because I'm mixing my x's and my thetas. I can integrate a function of x dx, I can integrate a function of theta d theta, but when they mix like this, I can't do anything. I have to resolve it one way or the other. So that's not going to end up being the direction we go. So it's a good thing to think about. So I take sine, cosine powers on their own terms. Right? The nice case is I can set up a sub for one or the other, and I can do that if either exponent is odd. Now I don't see an exponent of sine. I'm going to think of this as sine to the 0. My exponents are 0 and 2. Neither one is odd. Wouldn't you know it, we're in the annoying case. In the annoying case, what do I do with sine, cosine powers? I use my double angle formula for the cosine. So cos 2 theta. There's a little trip down memory lane here. Cos 2 theta has three things going on. It's cos squared minus sine squared. It's also 2 cos squared theta minus 1. It's also 1 minus 2 sine squared theta. And I can rearrange these last two to solve for cos squared and sine squared. The formula for cos squared ends up being 1 plus the cosine of 2 theta divided by 2. And that's what you got to do for even powers of cosine times even powers of sine. All right. So I can cancel a 2. Turn that 4 into a 2. So I can integrate term by term. The integral of 2 is 2 theta. And then I need the integral of 2 cosine of 2 theta. That's sine of 2 theta. So on the sideboard say, okay, so y is the integral of cos 2 theta theta equal to a half sine of 2 theta. Let's see. One thing, if you've done enough integrals of sine or cosine time where there's just a constant, you could probably just write it down and check it. Maybe you could just write it down and not check it for that constant. You can write it down, and when you check it, the chain rule kicks out at 2 and it cancels, and it's all good. If you're not quite up to that level of fluency, just do a U sub. It's pretty simple as U subs go. All right, so 2 theta plus sine 2 theta plus c. And now we're done-ish. Well, we're done with calculus. We did the integral. Now we got to do some more trig or algebra to get a final answer. Our question started out in terms of x. So we're not quite done when we write an answer in terms of theta. Right? Our assignment is to find a function of x with this derivative, and we're not there yet. So at this point, we have to go back here, where we relate x and theta, and figure out how to write these in terms of x. Let's start with the first term, 2 theta. So how can I write that in terms of x, given the information that we already have? I need to take one of these equations and solve it for theta somehow. And it turns out the inverse trig functions are designed to do that. If I take this and divide by 2, I can take an inverse sine can write theta this way. I could, if I wanted to, divide by 2 and have an inverse cosine. These actually end up being the same. I'm going to take this one just because it looks a little bit simpler. Or if I, if I really wanted to, I could write down an inverse tangent, but I'll skip that. All right. So theta is the inverse sine of x hat. Then I need to figure out what to do with the sine of 2 theta, which I don't have in my box. I have sine theta and I have cos theta. I guess those are back in this box. I have sine theta and cos theta. I don't have the sine of 2 theta. So I'm going to do a little side calculation here. I need to figure out the sine of 2 theta. And in order to do that, I'm going to need some trig identities. It's part of the mix when we have all this trig flying around. Now, I said there's only a few trig identities that you need to know. You need to know the double angle formulas and the Pythagorean identity, and that's about it. So this is one of the double angle formulas. Sine 2 theta is 2 sine theta cos theta. One of the top 3 trig identities. These I have expressions for in the box. That box, I guess. So 2 sine theta I know is x over 2. Cos theta I know is root 4 minus x squared over 2. I can cancel one of those 2's. So where I see the sine of 2 theta, I'm going to have x divide by 2 times square root 4 minus x squared plus c. So that's the integral of square root 4 minus x squared. All right, so I had 4 minus x squared. What if we turned it around and had x squared minus 4? It should be similar. Maybe. Actually, I'll mix it up, throw one of our curveballs in the mix, because we've got to multi-purpose our examples here. What if I had the integral of square root x squared minus 3 dx? This looks similar to the last one with 2 changes. One is the terms are flipped. The x is in front of the minus sign. That seems like it should be a pretty small change. The other is I don't have a square. I need 2 squares to get going in order to think Pythagoreanly, and I don't see them. Well, actually, maybe I do have a square, right? Is this something squared? Yeah, square root of 3 squared. So one of the things I may need to do to set up a trig set is kind of force something to be a square when it's not trying to. So if I'm thinking Pythagoreanly about this expression, the thing being subtracted from needs to go on the hypotenuse. Rather, its square root does. X squared means I want x to be my hypotenuse. And then the other thing being squared can go on either of the other sides. So that's how my triangle is going to get started. And then if I do the Pythagorean theorem, this expression here pops out as the third side. So I'm going to sub for an angle. Let's say I do this one. Actually, I'm going to do this one just to mix things up. I'll tell you why in a moment. It's actually going to make things a little bit easier. All right, so if I write down, say, the sine and cosine of theta tangent, I can see that the cosine of theta is root 3 over x. The tangent of theta is root x squared minus 3 over root 3. The sine of theta is root x squared minus 3 over x. So cut to it. Okay. Now, I want to solve for x in terms of theta. And if I rearrange this, I'm going to end up dividing by the cosine. X is root 3 times the secant of theta. So this is where I pause and explain why I flipped my angle choice. If I had picked this angle to sub for, x would be a cosecant. That's not really worse, but we spend most of our time with secants and tangents, not cosecant and cotangent. So in order to stay in my wheelhouse, I'm going to sub for this angle. X is root 3 secant theta. This square root that I was looking for, I can get by rearranging this expression. So the square root of x squared minus 3 is root 3 tan theta. And then to find dx, I need to differentiate. So the derivative of secant is secant times tangent. I have a sec theta tan theta d theta. All right, now I need to put all these pieces in over here. Square root of x squared minus 3 is root 3 tan theta. And dx is root 3 sec theta tan theta d theta. And if I simplify, I'm going to pull both of these root 3's out and combine them. I have 3 integral sec theta tan squared theta d theta. All right, so now I've converted over. I'm in Trigville, and I need to get my bearings, because there's a lot of different problem types in Trigville. This is a secant powers times tangent powers situation. There's the goal, the nice case, what we'd like to have happen, and then there's the 4 annoying cases, right? All right, so let's think about trying to do this the good way. If I want to substitute for a tangent, I need a secant squared to become part of my du. I don't have a secant squared, so it's a no-go. If I want to substitute for a secant, I need to peel off a secant times tangent, and then whatever is left had better be a function of secant. But what's left is just one lonely tangent. I can't convert it to secants because I need to do that 2 at a time. So neither of the substitutions is going to work out. This is the odd power of secant times even power of tangent yucky case. How do we do those? Well, I could substitute tangent squared to be secant squared minus 1 and expand it. Then I've got secant cubed minus secant. But then I have to know what to do with secant cubed and secant. Secant you should know from memory. It's sort of the most challenging basic building block integral that you should just know. Log of absolute value of secant plus tangent. What about secant cubed? Yeah,
Did the formula.
Yeah, there's a reduction formula for odd powers of secant in one of those weird little corners of integration. All right, now here's the punchline. Right, so if this is on a quiz as a trig sub problem, I'm going to have secant times tangent squared as one of the things I get, because that by itself could be most of the quiz. So at this point, I'm going to say they use x. It just so happens that I know that this is 3 times a half log sec theta plus tan theta plus sec theta tan theta. And how do I know that? Because I looked it up. Okay. And so I'm going to treat you the same way, right? It's going to be there. We'll actually run into sec times tan squared a few times when doing other stuff, finding lengths of curves or volumes or whatever. We'll run into sec tan squared. And when we do, I'm going to say, by the way, recall that the integral of sec tan squared is this thing. Oops, sorry, I'm putting minus sign. All right. So that step we'll get some help with, because otherwise this would be like 10 minutes just to do that. All right, so now I need to go back here and get everything in terms of x again. So, sorry, I meant to have a half. So the sec times tangent, here I can divide by root 3. Secant theta is x over root 3. So I'm kind of switching the order of my terms. I'm going to do this term first. 3/2 secant theta is x over root 3. Tangent theta is square root of x squared minus 3 over root 3. Let's see a cancellation here because these multiply to 3. And then minus 3/2 log secant plus tangent, that's x over root 3, plus root x squared minus 3 over root 3, plus c. There we go. All right, if you haven't already, note how the answer is a lot more complicated than the question. That's one of the things that's characteristic of trig subs, I think. All right. In the remaining 20 minutes, I want to show you a few wrinkles or complications or ways that this technique can get combined with other things. I'm not going to do all these problems out in quite as much detail, or I may skim through the trig sub itself a little bit faster. All right, so I'll tell you the punchline after I get to it. Let's say I wanted to do something like x squared of x squared minus 4 ds. Right. So if I see that integral, I'm going to be thinking about trig subs. Because x squared minus 4 is one of these patterns that I've trained myself to recognize. Jumps off the page. I'm hearing a voice in my head saying, Pythagorean theorem, Pythagorean theorem. So I'm going to think about this triangle, and maybe think about this angle, or maybe this angle, like the one we just did. And I'll just say, sort of, turns out I were to trig sub this thing, x is 2 sec theta, x squared minus 4 is 2 tan theta, and then dx is sec theta tan theta. I'm going to get something like this, times some constant that I didn't keep good enough track of. I think it's 8. Right. So I could do that. I could go through and wind up in trivial and a secant squared times tangent squared, and as trig integrals go, that's not too bad because I can substitute for the tangent and it's going to work out. But here's the punchline. I don't even have to do a trig sub for this problem. I can if I want to, but I can stay out of Trigville entirely. What's the other option here? Yeah?
Can you sub x squared minus 4 as like u?
Absolutely, yeah. So I can just go back to Calc 1, right? So the other option that involves no trig is just u equals x squared minus 4. du is 2x dx. So I have a half. This is part of my dx, u to the half. This is just a good old u sub, and fairly simple one as u subs go once you think that it's up for the inside there, right? So I can get a 2/3 u to the 3/2, and I end up with x squared minus 4 to the 3/2. I claim that you would eventually wind up in the same place here. Right? I said you could sub for a tangent, you get a third tangent cubed, and it turns out this is basically like a third tangent cubed. They end up in the same place. But the trig method is definitely the long way to get there. Okay. So one of the first admonitions is check u subs also. You may not have to do trig at all in a problem that looks trigish. See if you can save yourself. This is another one of the instances, sometimes you do 2 substitutions and you could have just done 1. Here I substitute for theta and then I substitute for tan theta. But I could just substitute for tan theta directly. And that's basically what this is. Okay, so that's the first section. Don't go to Trigville if you don't have to, unless you just really, really love it that much. As with other techniques, you may not be able to do u sub instead. You may need to do u sub also. Let's suppose I have something like this. This is changing it up a little bit because inside that square root, I see a 4th power. It's not a square. So that changes things. It's a little harder to write down a Pythagorean theorem here. But among the tricks that we've seen multiple times now in this class, x to the 4th is x squared squared. So one of the things I might want to do is create a more Pythagorean situation here by subbing for x squared. So if I sub for x squared, a square root with a 4th power in it becomes a square root with a u squared in it. And at this point, I'll just say then trig sub. This is very similar to the square root of 4 minus x squared problem from a moment ago. From here, it looks pretty familiar to the extent that trig subs look familiar. But this first step converts this into a more similar form. One of the WebWorks has something like this. The WebWorks that I'll assign for today, you have one version of the problem, something like this, in the denominator, and I'm going to think, hey, that's e to the 8x squared plus 1. I'm thinking about like a sum of squares here. This is looking kind of Pythagorean, but I need to substitute for e to the 8x. And then it's going to look like u squared with 1 squared. So you may need to do another substitution or something before it starts to look Pythagorean. The other thing that you may need to do before it really starts to look Pythagorean will be illustrated in the next example. So I'm going to hold back the punchline a little bit. This one is interesting because I don't see any numbers in it. And these things aren't both being squared, only one of them is. And if I try to do my normal techniques, it becomes challenging. I could try to set up a triangle, but it'd have to be something like this. And it looks kind of unpleasant. So there's something else I can do here. Maybe going way back to Algebra 2 memories. I have a quadratic. I want to write it with some squares involved. There's a technique called completing the square that's designed to do precisely that. So I'm going to complete the square. So rewrite this quadratic so that it involves a sum or difference of squares. So I see an x squared. I'm thinking about something of the form like x plus a constant. What if I were to square x plus a constant, x plus 1 squared, x plus 2 squared? If I take x plus a half squared, I'll get x squared plus 2 times a half x plus a fourth. Which is almost what I have in that square root. Almost. In general, the number that I'm going to put here is like half this coefficient, assuming that this lead term is 1. You can kind of work your way here with some guess and check if you don't have the pattern memorized. So if I write x plus a half squared minus a half squared, that'll cancel out. I have x squared plus x. So I'm going to use completing the square to recognize this is actually a difference of squares. I just have to work a little bit to see it. X plus a half squared minus a half squared dx. So as a bigger picture point, trig sub, the core version, you have a square root with things like x squared plus a squared, x squared minus a squared minus x squared. But anytime you have a square root, you might be able to massage it into a sum or difference of squares with some algebra shenanigans. Completing the square is one way to do that. So the place I probably want to go from here is substituting. If I substitute u as x plus a half, du is just dx, because the derivative is 1. This becomes square root of u squared minus a half squared du. And at this point, again, I'll say then trig sub. At this point, I'm set up for the more core version where I'm going to see something like this as my triangle. U is on the hypotenuse, subtracting a square of a half. Similar to our x squared minus 3 example from a moment ago. All right, one more. The wrinkles and complications category, and then I would say that's enough to absorb for one quiz. We most often are going to use trig sub when we see square roots. Actually, becomes one of our basic techniques now. If there's a square root, you at least think about trig sub. With these kinds of tricks, nothing under the square root may not even look that Pythagorean, but maybe we can make it so. But you can use without square roots. And in fact, this example is one of the things that we'll need next week when we head into partial fraction territory. Let's suppose I wanted to integrate something like 1 over x squared plus 9 squared dx. All right, now there's two things that almost work. Let me just tell you about the two things that, boy, if this were just a little bit different, it'd be so nice. What if this wasn't there? So I guess the 9 is still a little bit of an annoyance, but it's basically like an arctangent at that point. I guess with a little bit of massaging, it becomes just one of our building blocks. But it's squared. And no, we can't just say that the integral is arctan squared. It doesn't work like that. What if we had an x up here? Okay, the sub for x squared plus 9, it's like a 1 over u squared. Power rule and we're done. Unfortunately, neither of those is the case. So even though there's no square root, this ends up being a situation where trig sub comes to the rescue. And that sum of squares pattern still tips you off. It doesn't have to be inside a square root. So if I think about this triangle, drawn triangles very like this for a while now. I think about this triangle, I can still use it to make a substitution in this integral. So x over 3 is the tangent of theta. Right, opposite over adjacent. So x is 3 times the tangent of theta. And differentiating, dx is 3 sec squared theta d theta. So I'll need that to put in place of the dx. Square root of x squared plus 9 over 3 is the secant of theta. That's the hypotenuse over the adjacent. I can rearrange that, but I also want to square it. X squared plus 9, no square root, ends up being 9 secant squared theta. So over here, one over 9 sec squared theta squared, 3 sec squared theta d theta, and now I got to figure out how to do that trig integral. I can see some cancellations. Secant squared cancels with secant squared, although there's another secant squared left. 3 cancels with 9 squared, that'll be 1 over 27. And I can do at least the first round of simplification to get here. Okay, my constants come out to a 27, and I'm integrating 1 over the secant squared. How do you do that?
Rewrite it as cosine squared.
Good, exactly. 1 over the secant is the cosine. Yeah. So one of the things that we can do with secants and tangents, besides chase all those annoying cases around, is we can turn them into sines and cosines. And 1 over the secant is the cosine. And we actually did cos squared theta 30, 40 minutes ago, right? 1 plus cos 2 theta over 2. Integral gives you a sine 2 theta. You do some trig identities, and I'll just say then trig over the trig as before. We've already done cosine squared once, so I'll just refer you to that. And then backward passes. So here's an example where there's no square root, but the sum of squares should still suggest trig sub to you, especially if other things turn into dead ends. It's a good idea to check the u sub first. What if u is x squared plus 9? It just didn't work out. It's not bad to think about building blocks first, but it doesn't work out if it's not squared. So you still, when you look at this, you should at least think that trig sub is an option. And if the other options fail, you just got a trig sub, then you just got a trig sub. All right, so that's it. Quiz tomorrow. Trig integrals and trig subs. And plenty to learn, plenty to practice. Once you're over that hurdle, you can breathe a certain sigh of relief. That's probably going to be the hardest technique integration. See you then.